class, it's Mr. Hofstad here with lesson 8 of unit 5, our last lesson on our unit of circular motion and gravitation. This one is all about gravitational fields, and fields are actually a very conceptually hard part of physics. It's all about things acting over a distance without actually touching something. So we're all kind of familiar with this happening in our lives, whether it's with gravity between us and the earth, whether it's with magnets. There's all these things that act over a distance without actually touching. And the field of physics that works on this is this concept of fields. So today we're going to look at our most simple and most common type of field, the gravitational field. And this will kind of create a foundation for a lot of the other fields that you'll be looking at in Physics 30. So our first important part to get this idea of gravitational fields all worked out in our heads is how what we've already been calling force of gravity, right, or weight, is related to this idea of a field. So a weight we've been talking about for quite some time now. Right, we've talked about forces of gravity ever since Unit 3, and we brought in this idea of weight versus normal force and all of that as well. So we can now calculate weight of an object in two different ways. So this is what we have been doing all the way back from Unit 3, and this is what we introduced yesterday, or last class with Lesson 7. So here, our weight is equal to the force of gravity, right? Weight is force of gravity acting on a person or an object. And we could calculate the force of gravity using our new universal law of gravitation found on our formula sheet. We have our gravitational constant, capital G. Here we have, we're differentiating between the two masses. We've got our first large capital M. The larger M is the larger mass, so that'll be our planet, and M2, which is going to be whatever object or planet or whatever it is that is nearby, right? The object that is near the planet. So that could be us standing on the surface of the planet, and R squared is the distance between the centers, right? And here's why we're calling it R. Right, it's actually a radius between the center of the circles, right? And really important to notice that we're going from center of the circle to center of the circle, right? It's not from the inside edge or the outer edge or anything like that. It always is center to center. So make a nice highlight of that and keep that in mind whenever you are working with our universal law of gravitation. That's going to be our little tricky part of it. All right, we can also find the weight, as we have been up until this point, using the mass of the object times the gravitational field strength, right? So G before we just said was the acceleration due to gravity, which isn't wrong, but that is synonymous with our gravitational field strength. So we're going to abbreviate gravitational field strength from here on out as GFS, gravitational field strength. It's that lowercase g that we've been dealing with for a long time now. I think even since Unit 1 it was introduced. Right, and this is just our different ways of looking at gravity. So this is kind of a newer way, right? Weight per unit mass. When we rearrange, our force is equal to mass times acceleration, right? We now have acceleration due to gravity or gravitational field strength, which are synonymous, is equal to the force of gravity divided by the mass of whatever object we're trying to find the weight of, right? So it's always going to be a force over a mass is equal to, right, newtons per kilogram. All right, and if we break apart our newtons into its base units, its standard units, we can actually find that Newton per kilogram is equivalent to meters per second squared, So therefore, the gravitational field strength, lowercase g, our gravity, is also the acceleration of an object in free fall. So in order for that to really happen, we need to have no air resistance, no external forces acting on it, and then our object will be accelerating with the same acceleration as, right, our gravity, acceleration due to gravity. So this one is a little more known to us already. This one is just a manipulation of Newton's second law, going back to Unit 3. So let's try an example of this. We've got a planet, it's unknown, planet X. And on that planet, we have an object with a mass of 700 grams. I'll convert that to kilograms. We know it has a weight of 4.1 newtons. So in this case, weight is equal to the force of gravity acting on an object. Right? If you're ever not sure about that, just take a look at the units. It's given in newtons. So we're working with a force as a weight. We want to determine the max height if it's thrown up. VI, we'll say positive reference system where up is positive, down is negative. Positive 28 meters per second. We're actually kind of working with a kinematics type question again, going back to our first unit. Actually the second unit. So our max height, right, or max displacement from the start is what we're looking for. We have VI. If we think way back, we can possibly find a spot in our brain that remembers that when we're looking for a max height, we're going to use a final speed of 0 meters per second, because at that top point of its trajectory, right, in the y vertical direction, it actually needs to come to rest at the top, and then begin this negative velocity down, right? So VF is 0 when we're looking at that maximum height. All right, in order to solve this, right now we have 1, 2, an unknown. We need to have a third known variable, and that is going to be our acceleration. So first we're going to find our acceleration, then we're going to find that maximum height. In order to find this acceleration, we need to look at what we've just gone over in our notes about mass and weight, right? And remember that force of gravity is equal to mass times our gravitational field strength, or our acceleration due to gravity. We're going to rearrange this to solve for our acceleration, which is really acceleration due to gravity, because when this ball is thrown up, if we're assuming there's no air resistance, which the question explicitly says, the only force acting on it is gravity. It is in free fall. So we need to take our weight, divide it by our mass. We get 4.1 newtons over 0.7 kilograms, coming out as 5.857 newtons per kilogram, which can also be our acceleration in meters per second. So this was all determining acceleration due to gravity. Now we're going to take it and throw it into our kinematics equation to determine max height. And this has nothing to do with Unit 5 and everything to do with Unit 2. Physics is all interdependent. Nothing is really separate. It can all be combined into a nice rounded out question. So it's in free fall. We know that. Acceleration is equal to gravity is equal to 5.857 meters per second squared. Right? And that's going to be down, so we'll treat that as negative. So we have our VI, we have our VF, we have our acceleration. We're looking for displacement. We need to take out our formula sheet and find our equation. Actually, yeah, we're finding the equation that doesn't have time in it, which is our last one here. We're going to use VF squared is equal to VI squared plus 2AD. Solving for displacement. Displacement is equal to VF squared minus VI squared all over 2A. So VF was 0, VI was 28, positive because it's going up, squared, divided by 2 times negative because we're headed down, downwards acceleration of 5.857. And that gives us a displacement or a max height of 67 meters. A good review of Unit 2 combined with our new Lesson 8 material from Unit 5. Alright, got that one done. Now let's head on to the next page. We got a planet's influence on everything around it. Hopefully we're all kind of familiar with this idea already. Right, the gravitational field around Earth is influencing everything near Earth, right? If this could also be the sun, right? The sun is keeping all of the planets in our solar system in orbit through this gravitational field, right? It's actually the force of gravity because as soon as you throw a planet with a mass nearby, right? Let's say this is Earth. There's going to be two masses, the big mass and the little mass, and that will produce a gravitational force due to gravity, which is actually our centripetal force, producing our centripetal acceleration as we orbit around the sun. And here's kind of how gravity fits into uniform circular motion and why these are lumped together in the same unit. So, a planet can influence all masses that are near it. It acts at a distance. So this is a pretty groundbreaking idea, and it took scientists hundreds, possibly arguably thousands of years to come up with this field theory. And we could spend a whole course just talking about field theory, but we only get a little snippet here in Physics 20. Fields were essentially created in order to describe anything that's acting at a distance without touching. So they invented this idea of gravitational fields. It's more of a theory, really. So gravity is always directed to the center of the planet, or in this case, the sun, whatever you're looking at, the larger object. Right? Even if this is taken away, we still have a gravitational field. Right? It always exists as long as you have a mass. Even if we send a single atom of hydrogen out into a vacuum, it's still going to produce a gravitational field, right? And it'll always be directed to the center of the mass. So direction is always to the center, and this doesn't necessarily have to be a planet. This could just be any object. We just usually think about it in terms of planets and space. That's where we're most familiar with it. Next, the magnitude of any field will be shown by the density of the field lines. So the stronger the field, the closer the lines. If this were a really big planet, really strong field, we could have even more of these lines, these field lines, which are pretty much just vector arrows drawn in. You get the gist, right? So that would be a weaker field. This would be a stronger field. Strong, weak. Also, right, the magnitude of this is dependent on how far away we are from the mass. So the farther or the bigger this radius to the center of the circle is, the weaker the gravitational field strength. Inverse square relationship, right? Because the gravitational field strength is inversely squared with the radius. If we just look at our universal field equation, universal gravity equation. So to determine the gravitational field created by the central mass m, we use kind of just a part of our universal gravitational equation. So we're just removing our lowercase m, m2, because that would be the force due to gravity. Here we're just looking at a gravitational field. So that's going to be one of the trickier parts about this conceptually, keeping this idea about a gravitational field and a gravitational force separate. So a field is not a force. A field is always there, and it has the potential to create a force when a second mass is brought near it. So in order to find the field strength, right, independent of a second mass, we need the mass of our large object that is creating the field, in this case a planet, and we need the distance from the center of the planet. So the same distance away from the planet, right, if we're looking at the end of all of these lines, is going to have the same gravitational field strength, right? And we could also go much closer to it, and as long as we are the same distance away from that central mass, this red circle will have also an equal gravitational field strength, right? So we will notice that this gravitational field strength is independent of the test mass, our lowercase m2. So all objects experience the same g at the same r, right? And that's what I was getting at here. Any object placed on this red path will have the same g. Any object on the blue path will have the same g as any object that's the same distance away from it, right? But it won't have the same gravitational force because that's dependent on m2. So fields are not dependent on the test mass or the object that's brought near our central mass, but the gravitational field would be. Sorry, the gravitational force would be. Field would not. So that's a pretty key point, right? It's independent of our test mass, but it experiences the same gravitational force at the same radius. So we've been working with this essentially all semester. This is kind of an assumption because if you actually throw in the values for the mass of the Earth and the radius of the Earth, you'll find that it's really close to this value. You could be thinking to yourself right now, what if we're on top of the mountain? What if we're at sea level? There's going to be a difference. Yes, that's true, but it's going to be a small enough difference that we can use this average. Okay, this is our last example. Let's give it a shot. We want to know how far above the surface of the Earth we would need to be for a gravitational field strength. that would be our lowercase g, to be 5.8 newtons per kilogram rather than 9.81. So the farther away, or the bigger our R value, the distance from the center to center, gets, the weaker the gravitational field strength would be. So important here, we can find the radius and the mass of the Earth on our formula sheet. If you flip it to the back, it's under the constants. We've got the mass of the Earth as 5.98 times 10 to the 24, and the radius of the Earth as 6.37 times 10 to the 6 meters. So this is asking us, here's our Earth, here's the center of the Earth. We want to know how far something needs to be above the surface of the Earth. So that would be our distance, in order to have a gravitational field strength of 5.8. So we know G is equal to 5.8 newtons per kilogram. So we need to find the center to center distance. That would be our radius, right? It's going to get a little complicated because that distance incorporates the radius of the Earth and the distance above the surface of the Earth. So there's always going to be two parts when we're doing this type of question, right? There's the total distance from center to center, which is broken up into the distance from the center of the Earth to the surface, or the radius of the Earth, and the distance from the surface of the Earth to our object. So we know the gravitational field strength is 5.8. We're going to have to work with our gravitational field strength equation, which is essentially just removing our second mass from our universal gravity equation. And we're trying to solve for the radius here. So we'll have to multiply both sides by r squared, then divide by g. You get r squared is equal to capital constant of gravity times the mass of the Earth divided by our gravitational field strength. And then we'll just need to take the square root of both of those. So our radius, total distance from center to center, is going to be equal to the square root of our gravitational constant, 6.67 times 10 to the negative 11. Mass of the Earth on our data sheet was 5.98 times 10 to the 24. And our gravitational field strength in the question is 5.8. We're looking to see at what distance our gravitational field strength becomes 5.8. And it turns out that the center to center distance is 8.293 times 10 to the 6 meters. And that's going to be where a lot of people will stop and they will get the question wrong, because that is the center to center distance. We want to know how far above the Earth's surface we are. So we have to kind of create a little equation for what's going on up here. We know that that total center to center distance is equal to the radius of the Earth plus the distance above the surface of the Earth. And that's what we're actually solving for. So the distance above the surface of the Earth is equal to total center to center minus radius of the Earth, which is 8.293 we just solved, minus the radius of the Earth, which was 6.37 times 10 to the 6. So the distance from the surface of the Earth to the object above, where it has a gravitational field strength of 5.8 newtons per kilogram, is 1.92 times 10 to the 6 meters, which is, what is that, 19,000 kilometers above the Earth? Quite a ways. Oh, more than that. 100, a million. No. 19,000 kilometers, yeah. All right, hopefully the idea of fields isn't too overwhelming. It is a harder concept to get, but I wish you the best of luck wrapping up this unit and getting ready for your mid-test. Good luck.